So hello, thank you for joining us on this webinar brought to you by the McMaster Alumni Association. I'm Hamza, Khattak, a master's student in the Department of Physics, and I'm excited to answer all of your questions. There's a bunch of questions, and I'm going to try to answer as many as possible. So let's just get started. So the first question is from Jacob, a grade 2 student from Ottawa, Ontario, who asks what kind of molecules there are in soap. This is a great question because when you want to try to understand how things work, it's often important to look at the molecular perspective. So the one molecule that is in all soap is a surfactant. So this is what a surfactant molecule looks like. You have a polar hydrophilic head. Hydrophilic simply means water-loving, and we're going to explain what polar and non-polar mean in a bit. And then a long hydrophobic or water-hating tail. So just for people who might not know, polar means that one side of the molecule has a different charge than the other side of the molecule. So if we look at this little box here, this is a polar molecule because this side's more positive and this side's more negative. If you have both sides the same, so this side kind of cancels out that side, you have a non-polar molecule. So that brings us to questions from Mary, a grade 3 student, who asked why do we use soap, and Annika, a JK student, who asked how does soap work. So that molecular picture from earlier is going to become important now. So first, to why we use soap. Well, we want to clean our hands, right? Or clean some other surface. It might be some paint on it, some oil, some grease, some dirt, and we want to get rid of that. So let's look at what that oil looks like. So let's look at oil from the molecular perspective. So this is just a picture of some olive oil, and this is what fat molecules look like. There are these long chains of carbons and hydrogens. Sometimes there's double bonds here, but generally this is what it looks like. But what's important to note here is that these are non-polar molecules. So you have this little delta, it just means slightly positive. So you have little slightly positive hydrogens and little slightly positive carbons, but all of these cancel each other out so that overall your molecule is non-polar. Now, if we look at water, water is a polar molecule. So you have hydrogens now still with these slightly positives, but you have an oxygen down here, and the molecule has a direction. So there's more positives up here, and there's more negatives down here, so you have a polar molecule. So in the case of water, this means there's hydrogen bonding. So these hydrogens like to be around these other oxygens, and water in general likes to stick together a lot because it has strong intermolecular interactions. So interactions between different water molecules. Now, imagine this is the water and this is the oil. So all these water molecules want to stick together, and they want to stick together more than they want to stick to any oil. So you get the separation of the water and the oil. But if you look at this diagram more carefully, you'll notice that these molecules are being pulled down by other water molecules here. And if we add all of these interactions together, there's actually a horizontal force called surface tension at the interface between these two phases. So this surface tension is kind of like a film that's stretched across the interface of these two materials. And that prevents them from coalescing. And we want them to coalesce when we want to clean things up. So surface tension is a really cool phenomenon. There's a lot of interesting physics that comes out of it. So for example, there we go. So these water striders use surface tensions to stay afloat on the surface of water. So as you can see, in stay afloat, they can also jump off the water. There's actually a research group that's making robotic versions of these water striders, which is going to show up in just a second here. So, so surface tension is really cool phenomenon. There's a lot of interesting physics that comes out of it. So for example, there we go. So these water striders use surface tensions to stay afloat on the surface of water. So as you can see, in stay afloat, they can also jump off the water. There's actually a research group that's making robotic versions of these water striders, which is going to show up in just a second here. So this is a surface tension can be used for locomotion. So here, these are robotic water sliders, and this group's been able to use the robotic water sliders to jump up. So surface tension is a force that's associated with interfaces, energy cost associated with the interface of materials. What soap does is it disrupts these interactions between different water molecules. So it makes these interactions weaker so that the oil and water start to, the surface tension is decreased and the cost of the interaction is lower. These long hydrophobic tails can be in the oil, and these hydrophilic heads can be in the water, and you decrease the surface tension. What this means is that the soap molecules can surround the dirt and oil, forming micelles, and now what you can do is you can simply wash off the water, and by washing off the water, you wash off the dirt and oil. There's a lot of other cool phenomena that come along with surface tension as well, though. So for example, the Marangoni effect. So I'll play this video here, see what it's about. So remember that surface tension is kind of a stretchy force. So I put some pepper and some water. So why do you think this phenomenon could be happening right now? So if when you put the soap in the middle, all the pepper goes to the side. Let's place it out again. So similarly, you can make a soap-powered boat using this Marangoni effect. So this is just probably some distilled water, and you put a little bit of soap on the end of a stick, and the boat's propelled. So we're thinking about why this happens. We remember thinking about surface tension as being a pulling force. So when you add the soap, your surface tension decreases. So it decreases to a point where it's less than the surface tension of the surrounding material. So then that surrounding material with this high surface tension can pull on the material with low surface tension, and you get the movement of the surface liquids to regions of higher surface tension. There's a lot of cool experiments with this. This is a really fun video, so I'll show you this. But this effect called Marangoni bursting is caused by this effect. So you put these alcohol droplets in oil, you get this really cool, beautiful formation of droplets. And this happens because of Marangoni flow and evaporation. There's lots of stuff online if you're interested more in learning about this type of phenomenon. So next, we move on to Ella, a grade 9 student from Hamilton, who asks, is there a chemical difference between dish soap and hand soap or body soap, or is it just marketing? And Nash, a grade 3 student from Grimsby, who asks, is there a difference between bubble bath and soap? So these are great questions. A lot of stuff is about marketing, so let's look at if this particular case is that's true. So I went online and looked up the ingredients for a common dish soap and a common hand soap, and as you'll see, this sodium lauryl sulfate ingredient seems to show up in both of them. And if we look at what sodium lauryl sulfate is, it is that surfactant molecule. So it's that molecule that does the cleaning. So it's that soap molecule. Technically, it's a detergent, but we won't worry about that. So looking at this, you might think that they're all the same, but the quantity of these surfactants can vary between different soaps, and there's also other ingredients that affect the properties of the soap, for example, to reduce irritation in the skin or add other cleaning properties. So generally, hand soap will be more gentle than dish soap, and then body wash will be gentler still. So there are differences between the different soaps. And bubble bath usually is a very, very mild soap. The next question comes from Lucas, a grade 3 student in Alberta, who asks, what makes natural soap different from other soaps? And Kailong, a grade 2 student from Dundas, who asks, how can you make soap? Well, the thing that makes natural soap different from other soaps is the ingredients. So the actual work as soap as a cleaning agent is the same. It's just that in natural soap you'd use, for example, olive oil or butter or some other animal fat, whereas in sort of a non-natural soap, which are referred to as detergents, you usually use a petroleum-derived product, but the cleaning effect is the same. Now, to make it, natural soap is, you can make it at home. So what you do is you'd mix some olive oil, which has a chemical structure that looks something like this, with lye. So if you'll notice, this chemical structure has these long chains attached to this what's known as a glycerol. We'll turn into a glycerol here. This lye is able to split this up into the surfactant and this structure here, which is known as glycerol. So this is how soap's been made for thousands of years. So there's evidence of soap being made in ancient Mesopotamia, like in 2000 BC or earlier. So soap's been around for a long time, and that's the natural way of making soap. Now, if you're interested in making soap at home, there's some more processes involved. So you have to precipitate out the soap, and you have to sometimes balance the pH, and there's a lot of guides online on how you can do this, and there's different methods as well. The next question comes from Lucas, who is a grade 3 student from Alberta, who asks, why is some soap liquid and why is some soap solid, and is one better than the other? It's a great question. So in terms of cleaning properties, both liquid soap and solid soap work very well. So it's important to hand wash. It's more a matter of personal preference whether you use solid soap or liquid soap. Some people find that liquid soap is less harsh on their hands, but it's personal preference. However, the liquid soap itself has a lot of interesting properties because it's a complex non-Newtonian fluid. So just this video is going to show you something about that. So start it up. So we have these two syringes. One has a regular liquid, so like water, for example, and this has a non-Newtonian, it's referred to as a shear thinning liquid. I'll explain to you what that means. So when you squeeze and apply what's a shear force to the liquid, they both flow. However, when the shear force goes away and there's not much of a shear force, the small shear force is able to push that regular liquid, but the non-Newtonian liquid, the shear thinning liquid, stays solid. Ketchup is another example of a non-Newtonian liquid, and it's also shear thinning. So a cool effect that you can get with these non-Newtonian liquids is known as the K effect. So this is a stream of shampoo, for example, falling on some surface. So as I play this, you'll see that there's these cool streams that sort of point back upwards out of this falling stream. So if we look closer at this, because the material is shear thinning, see, little divots form, which redirect the motion of the stream of fluid. So this is in slow motion, so we'll see that happening. It's hard to see the actual divot forming, but you see the fluid comes in and then it's redirected in another direction. There's a lot of explanations for why this happens, and it depends on the different materials. It's still an active area of research, but one example is that for polymers, you have a bunch of little chains moving everywhere, and some of you may have heard Carmen's talk, which may have discussed some of this, but these chains are entangled with each other, and when you apply a shear force, they kind of elongate, and the entanglement's not as strong, so they can flow. The opposite of a shear thinning material is a shear thickening material, so getting a bit away from the soap, but this is a cornstarch mixture, and if you'll notice, if you just put it slowly, it'll flow down, but if you pull it hard, it acts more like a solid. So this is a shear thickening material. I'll show you the. If you smash it, see it's hard for a bit, and then it flows down into it. There'll be a little slow motion video of that going on as well. So these liquids can have these cool non-Newtonian properties, and people who design materials like soap try to engineer in these properties to better suit their purpose. The next question comes from Mac, a grade 2 student from Waterdown, Ontario, who asks, how does soap kill germs? Well, there's a great illustration from the New York Times on how this works. So coronavirus is an example of a germ, and lots of germs have these similar properties. So surrounding one of these bacteria or viruses is often a lipid bilayer. So this is essentially oil bilayer. So you have layers of long chains of molecules, and then what these soap molecules are able to do is get in these lipid bilayer molecules, because remember, they have a hydrophobic tail, and they're able to pry open the lipid bilayer and destroy the bacteria or virus. In this case, releasing the material and destroying it. The other mechanism by which they can clean is by the just standard mechanism that soap works, where it gathers up a bunch of oil and dirt in these micelles, and then it's simply washed off. So you have sort of a two-pronged approach on how it defeats germs. The most important thing about that is, though, making sure that you get a good coverage of soap. So just in case anyone hasn't seen things like this, just a cool demonstration on how you should wash your hands. So you have to get coverage of your entire hand, because the germs can live everywhere, and you need to get the soap everywhere. So you do that, you have super clean hands. Olivia, a grade 4 student from Dundas, asked why you have to rinse off soap but not hand sanitizer. So people are familiar with using hand sanitizer to clean and also using soap to clean. So you might ask why the mechanisms are different. So ethanol can also disrupt those lipid membranes, and ethanol is what makes up hand sanitizer. But if you look at the chemical structure of ethanol, so as we talked about earlier, the molecular structure is important to understand. So ethanol is a fairly small molecule, whereas these soaps are fairly large molecules, and they rely on water to work. So this depends on a lot of other things, but in general, larger molecules have larger van der Waals intermolecular interactions, and they like to stick together more, so they don't boil off as easily. So ethanol will boil off easily, which means it's going to evaporate easily. So once you wash your hands with, or not wash your hands, but rub your hands with some hand sanitizer, it can evaporate off, whereas the soap won't evaporate off. And as we mentioned earlier, soap needs water to work. So the next question comes from Nash, a grade 3 student in Grimsby, Ontario, who asks, how does a bubble bath make all those bubbles? And Lauren, a grade 5 student from Ancaster, who asks, why does some soap foam more than others when washing your hands? Well, the science of the formation of bubbles in soap has seen actually a lot of interest in recent years. It's an old field, but it's also a lot of interesting new stuff going on in it. So in terms of why it forms bubbles, so we talked about that surface tension before, right? So it's like a little stretched film. So another example of a stretched film is a balloon. So if you fill this balloon with air, that stretched film keeps everything inside. And the surface tension does kind of a similar thing for water droplet or air bubble. The thing that the soap helps with is stabilizing this these bubbles. So the soap molecules heads are in the water and the tails are sticking out. And it's actually based on Marangoni flow, where you have liquid flowing to thinner areas, which helps stabilize these bubbles. In terms of the foam, there's a lot of interesting research into understanding what properties affect the formation of foams, what parameters affect the formation of foams, and engineers try to design materials such that there's more or less foaming. They can try to decrease the foaming, which is important in some circumstances. And this is something that's still going on today to understand why this happens. So final questions from Samantha, a grade 7 student from Mississauga, Ontario, who asked, could soap bubbles be made permanent? Well, let's take a look at a soap bubble and what are some of the properties affecting it. So if we look at from a molecular perspective again, so we have these soap molecules and a layer of water between them that forms a soap bubble. So what causes this bubble to be destroyed? So there's a few things. There's drainage. So the water wants to flow downwards, right? So then the top of the bubble is going to get thinner and thinner with time. There's also evaporation. So the water is going to evaporate. That's also going to cause the bubble to be destroyed. And lastly, if it touches something, it can cause a rupture. So we can't completely eliminate or stop these things from happening, because eventually the bubble is going to evaporate or it's going to drain. But what we can do is sort of slow a lot of these things down to make longer lasting or larger bubbles. So this is an image of sort of the drainage effects. So you see different colors represent different thicknesses. So the bubble drains downwards, and we want to try to prevent some of this. So what we can do is use polymers. So these polymers entangle with each other and help stabilize the bubble, so that once it stretches, it's less likely to break up. And in fact, using this technique, we can make giant soap bubbles. So this is an experiment of supergiant soap bubbles. So you can do this at home. You need a common ingredient is guar gum, which is a polymer which helps sort of keep the bubbles from breaking up, and you can make these supergiant soap bubbles at home. I'll play this video a bit more. Just another experiment you can try at home, making these giant bubbles. So the polymers help keep the bubble stable when it starts to stretch because of the drainage and the evaporation. There's just some more video on giant bubbles. So I hope you've learned something new today and can share your newfound knowledge with your family and friends. Thanks for joining us, and we'll look forward to answering your questions in a future session of Ask a Scientist. Thank you.